In this video, we will talk about evaluate performance of a classifier in Python using confusion matrix. So when we have to train and classifier in Python using scikitlearn, then there is a performance matrix called confusion matrix, which can be used to evaluate the performance of a classifier. In the confusion matrix, it lists how many counts of the data have been trained correctly and how many counts of the data are not trained correctly. So the general idea is to count the number of times instances of, for example, class A are classified as class B. So in confusion matrix, each row represents an actual class. So this is a confusion matrix. So each row is actual class for the negative or positive. And each column represents the predicted value for the negative or positive. So this area lists the counts of each category. So for example, if you want to know the number of times the classifier confused images of 5s as 3s, so you would look in the fifth row, because the fifth row represents the true class is 5. And the third column, because of the third column represents the predicted value is 3. So a perfect classifier would have only true positive and true negatives. So its confusion matrix would have non-zero values only on its main diagonal. So this is true negative, which means the actual value is negative, is for example, non-5, and the model also classified as non-5. So this is true negative with green color. And this field, the counts represents the true positive, because the actual value is positive, and the predicted value is also positive. So these two yellow area represent the counts for data are not classified correctly, though this is called false negative. So we predicted the value as negative, but actually it's positive. And this field represents the false positive, because it is predicted positive, but actually it's negative. So in statistic notation, this area also called type 1 error, because the model take it as significant, but actually it's not significant. So there's error. And this place in statistical notation is called type 2 error, because the model does not find actually its positive value. It's missed the positive value. So if we take a very simple practical example, for example, we want to find the criminals. So this place represents how many criminals. So this is actually the criminals has been caught, but this represents the criminals have not been caught. And this row represents non-criminal people. So this is classified as non-critical people, but this area represents non-criminal people have been caught, taken into prison. Right? So the confusion matrix also gives you a lot of information, but sometimes you may prefer a more concise metric. So an interesting one to look at is the accuracy of the positive predictions. Though this is called the precision of the classifier. So precision represents the true positive divided by the true positive plus false positive. So this is This is the true positive. Then true positive divided by the yellow one and the green one. So which means the precision, which means the module classified as positive. But how much percent of this classified as positive is actually positive? So we have to use this one divided by the sum of yellow one and green one. And another metric is called recall, also called sensitivity or the true positive rate. So this is the ratio of positive instances that are correctly detected by the classifier. So the formula for the recall is true positive divided by true positive plus false negative. So the recall is the idea which I have talked that how many criminals have been found, have been caught. So we have to use the true positive divided by the true positive plus false negative. So this is the criminals missed, right? So true positive divided by the sum of true positive and false negative. So the precision takes into account the column of this column, but the recall takes into account this row. So next we will show some code in Python. First, we will review quickly to run a binary classifier for mixed data with images, and we classified images as 5 digits and not 5 digits. So first we import the module and set the working directory. Import the module, set the matplotlib, and set the savefig function. We will run this code very quickly. If you are interested in, you can check the video description and find the link for the file. We load the data for the mixed from OpenML, and actually the module classification has been shown in the previous video in this playlist. So you can check if you're interested in. So here we will run very quickly, not because we focus on the confusion matrix in this video. So we show some digits. Then plot the digits, then plot rows of digits for the 100 digits. This is the mixed data for digits from 0 to 900 written data, which in this model we use to classify as 5 as not 5. So for example, these are not 5, this is 5. Then we set the training data and test the data. So we set the data as the target data as y equals 5 or not, and y equals 5 here. For the test and the training data. Then we load the module SGD statistic gradient descent classifier from scikitlearn. Then train the module with a tolerance and with iteration 1000. So training the module using set first to create an instance of SGD classifier of this class. Then we use the fit function in this class. Take 1 minute. So model trained, then we can use the trained model to predict some digits. Some digit actually is 5 digits, so the result for the prediction is true. Then next we can evaluate the performance also using one type called cross validation using 3 folds. So in each fold, so the training data will be divided into 3 parts. So each part called folds. Then we will run 3 times. In 3 times, we'll take different folds as the test data and train on other folds. So there is 3 situations, 3 results in cross-validation. So the results for the accuracy for the 3 folds is this result. Then another type is also use a cross-validation, but use a stratified sample, which take into account how many 5 in data and how many data are not 5 in the training data. So here we load the model for the stratified folds, and we'll run again cross folds, but this time we're taking into the stratified sample. So here we just quickly skip the process of set up a classifier and train a model. And the detail of this part of the code and an illustration can be found in previous video in this playlist. If you want to interested in, check the playlist of this video. So the result for the stratified are a little different from the previous cross-validation. So this next model is called 0 model or base model. Actually do nothing, just predict odd is negative. So we will show the results about 0, 90. Because the only 10% of the data are 5. So if you actually do nothing, just all the taken as negative, you will get 90% of the accuracy. So this is why accuracy is not necessarily can say the model, the performance. So that's why we will use the confusion matrix. So from this line of code, we will focus on the confusion matrix. First, we will import the module called predict. Cross-validation predict, then we'll create the results of the predict with the cross-validation. Actually, this is focused on only training data. So here in the confusion matrix in this video, we focus only on the training data. So the X train, Y train. We do not use the test data, which has been used in classifier before for another video. So next we import confusion matrix module, then use the result of the prediction we have created here, then with the actual target value of the one train. So this will create this confusion matrix. This is true negative, this is true positive, this is false negative, this is false positive. So if we show this line, you can see there about 5,400 data for the image, actually digit 5, and about 10 times more, about 54,000 are not 5. So only 10% of the data 5, right? Then if you want to just use 135 is the target value as prediction, then you can get and perfect confusion matrix. So we should code here. So this is a perfect confusion matrix. 5,421, 5 digits are correctly classified as 5, and 54,579 digits image not 5 and actually classified as not 5. So this is perfect. Then the code will show the precision and the recall. So from scikitlearn module, import precision score and recall score. Then we can create precision score using precision score with Y-chain predict and Y-chain actually the real target value. So about 0.73 for the precision. Then we can also manually calculate the precision from confusion matrix. Just use the formula we have seen in PowerPoint page. We get the same result if we calculate manually. Then similarly, we can calculate the recall score using recall score function. And also can manually calculate the recall score function from the confusion matrix. We can get the same results. Then we take a look at PowerPoint again. So there's another score called F1 score, which combines the precision and the recall into a single metric called F1 score. So in particular, if you need a simple way to compare two classifiers, the F score is the harmonic mean of precision and recall. So whereas the regular mean treats all values equally, the harmonic mean gives much more weight to low values. So as a result, the classifier will only get a high F1 score if both recall and precision are high. So F1 can be calculated as 2 divided by the inverse of precision and plus inverse of the recall. So actually this is the true positive, true negative, true positive in numerator and true positive plus the half of false negative and false positive in the denominator. So if you want to calculate the F1 score, have to import the module. First, for F1 score from scikitlearn, then you just can use F1 score function to calculate about 0.74. So this is actually a harmonic mean because the precision is 0.72 and the recall is 0.75. So harmonic mean is between these two, right? And you can also use the confusion matrix to calculate the F1 score manually. Same results. So the F1 score favors classifiers that have similar precision and recall, but this is not always what you want. In some contexts, you mostly care about precision, and in other contexts, you really care about recall. So for example, if you train a classifier to detect videos that are safe for kids, you would probably prefer classifiers that rejects any good videos, low recall, but keeps only safe ones. So because the kids are very vulnerable, so we have to keep the kids safe. So what you classified as safe images, safe videos for kids, you should 100% make this video is correctly classified. So in this case, we want the precision is very high. We do not care about the other videos that's not classified as kids is correct or not. We only care about the videos that are classified as safe for the kids is actually safe, right? So this is very important. In this case, we want a higher precision. So, but in another classifier, you may want a higher recall. Do not care really about on the precision. For example, in another case, you want to use a classifier to detect shoplifters in surveillance image. So it is probably fine if your classifier has only 30% precision as long as it has 90% recall, because you want to find old shoplifters. But the percent of the correct positive in your classifier may be very low. But actually you find old shoplifters, right? So this is high recall and low precision. Unfortunately, you cannot have it both ways. To increase the precision, sometimes will reduce recall. And if you increase the recall, sometimes you will decrease the precision. So this is called precision recall trade-off. So to understand this trade-off, let's look at how SGDC classifier makes its classification decisions. For each instance, it computes a score based on decision function. So there is a score for each observation, for each instance in training. So the decision function will make it positive or negative based on the score and the module. So if that score is greater than a threshold, it assigns the instance to the positive class. Otherwise, it assigns it to the negative class. So the classifier module will create a score for each instance. And actually, we can show a threshold. So this threshold, if set very high, very low, then the same score will get different results for the positive, negative, right? So this is the figure. Shows the few digits positioned from the lowest score on the left to the highest score on the right. So this is each digit, each observation, each instance. There is a score from the module. So 8 has a score very low, and this has a score in the middle, and this observation has a score very high. So suppose the decision threshold is positioned at the central arrow between the two fives. You will find 4 true positive on right of the threshold and 1 false positive, actually 6. Therefore, with that threshold, the precision is 80%. But out of 6 actual fives, the classifier only detects 4. So the recall is 67%. So what does this mean? So if we set the threshold here, because the score is fixed for each observation, right? If we set threshold here, so this 5 instance will have the score higher than this threshold, will be classified as positive. So will be classified as 5. So 5 classified as 5, but actually 4 is correct and 1 is not 5. So the precision is 80% here, right? If we set the threshold here, and from this area there are 2 5. So because total there are 5 digits, of 6 actually 5, but 4 classified as 5 and 2 missed because we set a threshold here. So which means in the recall there are about 4 of 6, means 0.67%, right? So if we raise the threshold, so move it an arrow to the right, the false positive 6 becomes a true negative, thereby increasing the precision with 100%, but when true positive becomes a false negative, we decrease the recall to 50%, right? Sorry. So if we increase threshold to this line, then only 3 digits will be classified as 5. So this is correct, all are correct. So 100% precision, but we missed 1 more digit of 5. Actually 3 are missed totally, right? There only recall for 50%, so recall is lower now. So if we move here, the recall will be higher. All 5 will be classified as 5, but the precision normally will be lower. So the precision and the recall cannot be increased both or reduced both. They trade off between these two metrics. So the question is, how do you decide which threshold to use? So in Python code, we can use the cross-val predictor function to get the scores of your instance in the training set. But this time specifies that you want to return decision scores instead of predictions. So we can use a code called decision function in cross-val predictor function. So with these scores, use the precision recall curve function to compute precision and recall for all possible thresholds. So next we can actually use this code, plot a precision recall curve against the threshold. So this is the precision recall and precision on the y-axis, and x-axis is threshold. So we will show this code in Python. First, for example, we get the y-score using decision function for some digits. The some digits, this is the individual observation. Each score is 2412. Then if we set the threshold 0, then the result of the prediction will be true. True, right? Because the score larger than 0. But if we set the threshold is 8000, then the result is false, because the score is lower than 8000. So we can actually get all the scores using this function and set the method the decision function. Take a minute, go see the module for the predict module. Then we can import precision recall curve module, and using this module to run to show the precision recall curve. So this is actually the same figure, precision recall curve, as in the PPT page. So from this curve, you can see the precision recall curve trade-off, right? So another way to select a good precision recall trade-off is to plot precision directly against the recall. We can also do it in Python. So this is the precision against the recall. So we find the best point according to the model project requirement. So you can see that the precision really starts to fall sharply around 80% recall. From this point, the precision will sharply dropped, right? So you will probably want to start a precision recall trade-off just before that job. For example, around 60% recall. But of course, the choice depends on your project. So suppose you decide to aim for 90% precision. You look up the first plot that finds that you need to use a threshold of about 8,000. To be more precise, you can search for the lowest threshold that gives you at least 90% precision. So what this means? So we have seen the threshold increased, the precision will be increased. So we just lower the threshold until we get the 90% precision. So we can select this threshold and see how much is the recall, right? So in Python, you can perform this using threshold function. In amp.argmax with the precision large equal 0.90, then this will return the index of the threshold list array. Then we'll get this threshold. We show this threshold 7,800. Then upon this threshold, we can get the prediction value of this module. We set 90 here because we want precision 90, right? Then can show how much is the precision. Of course, it's 0.90 because we set the threshold according to this value. So also we can show how much is the recall. Recall is about 0.43 now. You can see the precision 90 is about 0.43 for the recall. So in summary, in this video, we're talking about confusion matrix and precision recall and their trade-off. So if someone say, let's reach 99% of the precision, you have to ask at what recall. So the only precision or only recall itself cannot necessarily show the performance. You have to take both in classification module, in machine learning, right? Thanks for watching this video. Thanks.